Good morning, everyone. Nice to meet you. So it's very pleased to have this chance to present our group the recent result regards a layered division multiplexing system with index modulation. So a layered division multiplexing system is quite popular in recently, especially for the broadcasting system and also for the 5G system. So they can support the different modulation for different users at the same band. And so in this case, for the new 5G new radio, they also propose some like the power domain multiplication for regards the different users. So first, I gave some introduction regards the layered division multiplexing LDM. Actually, this is quite similar to the popular LOM-IM modulation as well. And also another modulation, index modulation, how to combine the LDM and also the IM together. And then I will provide the simulation framework for our research regards the LDM system and also the IM system. And also the example codebook for the combined LDM and the IM. And also the simulation results and also the theoretic development regards the symbol read error. So we compare the theoretical model results and also the simulation results altogether to provide the similar results regards the averaging error for LDM-IM system. And also we compare the transmission rate regards the bit per channel use. So LDM system, so ideally, LDM system, the basic idea is to introduce the different power of the modulation at one channel. So in this case, different users can use the different power level of the transmitted signals. So in this case, when you decode the LDM system, you need to decode one layer individually, and from top to bottom. So at receiver, you need to consider the up layer decoded first. So lower layer is the interference for the up layer. And after the up layer is decoded, you need to do the cancellation. So you do the cancellation to cancel the up layer to decode the one layer down. So from the top until the bottom. So when you design the power level of each individual layer, you need to carefully design what's the SNR you need to handle between the different layers. So another modulation, popular modulation we used, also they called index modulation. So this is also the popular modulation scheme they used currently, especially for the 5G system and the 5G beyond. So the index modulation explores the index of the OFDM subcarriers, so as an information barrier to transmit extra bits. So in this case, okay, when you put your data onto certain index of the OFDM symbols, so when you take this as information, so you can put the coded read or coded bits for that information. So you put one extra information when you put on your OFDM symbols. So we call this is like an index modulation. So for this example here, so if you look at this example here, the O1 is like information bits. You can regard like this is regards like information bits. One of the, you can have 2 bits 00, 01, 10, 11. So O1, you can regard this as for index 1. So if you put the data at the index 1, that means this information bits 01. So when you detect the channel at the receiver, if you detect a channel, you have information at index 1, that means this means information bits 01. So this is a very simple example for index modulation. So for 4 channels, it's a 4 subcarrier. If you put data at the subcarrier 1, that means you're mapping into the information bits 01. So here you don't need any extra modulation, just to select the subcarrier to regard like a QPSK or BPSK. It's the simplest one. So existing research, there's 2 different for the LDM, the popular. One is to combine the MIMO, especially sometimes regards the 5G direction, it regards the LDM with massive MIMO systems, or normal with a massive MIMO systems, to improve the capacity of the channel. So another one is a spatial modulation. So spatial modulation added with LDM. So for the index modulation, actually we need the optimization to subcarrier selection. So how to select the subcarrier carefully or intelligently to improve the better error performance. And also the index modulation combined with the MIMO. So how to combine the MIMO, especially for massive MIMO systems, to the better capacity or diversity gain. And also the detection, how to improve the detection for the better error performance. So this is a research for the index modulation. So now our proposal is to, okay, can we combine these 2 different research directions together? So we introduce the layer LDM with index modulation. So this is our framework for the system. So we build a system. It's a 2-layer LDM-IM systems for the transmission. So at the transmission side, we have a up layer. So we set up like 2 layers. So up layer, 1 up layer and 1 low layer. So 2 layers combined together to provide the 2 users to access at the same time. So 2 users. And before we do the LDM part, actually first we split the 2 bits to provide for the index modulation. So we combine the index modulation and the LDM together. So provide before we do the OFDM, the IFFT, we first to combine the IM data and the LDM data together, and then to IFFT. So, and when we combine, we have a codebook. So this codebook mapping will provide the IM mapping into the different subcarrier. So at the receiver side, also after the FFT, we need to split the bits. First, split the first part is index bits. And then we do the cancellation for the LDM. So then when we go into the bits, for the information, we need to combine the index modulation part and also the LDM modulation part. So the first part of the up layer and the lower layer are combining together as the index bits for the index modulation, the first part. The second part is modulation for the traditional, the QAM modulation. And then the LL, so no layer symbol inject into the up layer. So here, the multiply with a different power level and add together for transmission. So this part is the LDM part. So this part is IM part, and add together LDM and transmission. At the receiver side, the decode part. So for example, this is a At the receiver side, the decode first goes the index demodulation and then for the LDM demodulation. So that's one part. For the IM part, the subcarrier need to have a detection. So the subcarrier detection will detect which channel is active for transmission. So in this case, you can detect what's the information bits you used for the index modulation. And also for the receiver part, there's a very critical part is for the interference, for the low layer cancellation. So when we decode the layered modulation, how can we cancel the signal with up layer? And then we will get the information bits. So combine this together, we can get information bits, up layer and the low layer. So this is the example code book we use for the index modulation. So the subcarrier, this is an example for 4. We used for 4 subcarrier, you will have 2 bits. So 2 bits you can represent. And for this 2 bits information, you can represent which channel is active. So when you detect the active channel, you can find the represented the bits for the index modulation. So example, so when we do the simulation, for transmitter side, the input, so assume the input bits for up layer and low layer and 11, 11 and 01 separately. And the index bits allocated for the up layer and lower layer both 1 bit. For example, this is a 11, this is up layer, and the 01 is lower layer. So the 2 segment, the first one is index. The first 0 is index. So in this case, this 10 is the information bits for the index modulation. And the second part is information bits for the traditional cram for the LDM. So combine the first segment of the up layer and the lower layer, 10 for the IM, and then according to the symbol code book, the active channel you can select for the OFDM is a second channel, you can see. Also second channel, and then modulated the second part. So in this case, in this example, the second part is 11. And same with the traditional cram. So it depends on what's your modulation you need. You can use a BPSK, QPSK, or 14 quant, or 16 quant, or 64 quant. And this will be obtained the LDM part. So LDM part, we can up layer and lower layer symbol. So when you construct your layer symbol at a lower layer, but you need to adjust the power level, because in order to detect the different users, so we use a different power level for the together to construct the LDM symbols. So we have a different injection power for different users. Then we can map in the active channel. So now because active channel is selected based on the index modulation. So now you can put your modulated LDM symbol into the active channel. So by this action, you have 2 parts of information bits. First is the indexed modulation information. Second is your LDM modulation information bits. Now, after that, the signal now is converted to the time domain by IFFT. So in this case, your OFDM symbol here, you have 2 parts information. So when you decode it, you need, before you do the traditional LDM decoding, you need to do the index demodulation first. So for receiver, assume the active channel can be detected without error. So here we ignore the detection issue. So we assume we can perfect detect channel, active channel to get the data. So for every detection, we can successful to get the information bits for index modulation. So then the received symbol you can consider, you can successfully get the information bit symbol at the selected channel. So when you detect this with a symbol codebook, the bits you can get from the index modulation is 1, 0. So before you do anything, before you do any decoding for the LDM, you already recover 2 bits information. Here is 1, 0. So 1, 0 is beginning. And also, okay, now you need to do a second part is for the LDM part. So you need to calculate the different LDM symbols with the upper layer and the lower layer. So the received signal here we consider as a channel. So here channel is a traditional Rayleigh fading channel with a Gaussian noise. So here, if we consider the YS here, you have 2 parts. Okay, the received symbol, after channel, you will always have 2 parts. So one is upper layer for one user, and one is a lower layer for another user. They may use a different modulation, or they may use a different power level. So when you decode it, then the detect the upper layer. Okay, we can just simply regard the lower layer as interference or noise. So we can derive our error rate based on the maximum linear likelihood detection. So the minimum received signal and remove the channel effect. So here the index UL means the upper layer, and the X dash means the received signals, and H is the reverse, also reversed of your channel. So you can successfully obtain the received symbol for the upper layer. And for the lower layer signal, YLL here means the lower layer signals. You just need to cancel the upper layer by, this is actually received, YUL, Y upper layer actually equal to the received signal. Just take away your upper layer transmitted signal over the channel. So there's 2 detection. So first you detect the low upper layer. Second, you need to do the similar maximum likelihood detection for the lower layer again. So you need to detect twice. So here we only got 2 layers, so detection only twice. So use the same detection again, to recursive to the detection again. So we can demodulation to detect the received X dash LL. So X dash LL here means the recovered received low layer symbol. And then so after the received symbol XUL and XLL, we can successfully use the demodulation to get the bits. And the bits now B-UL and B-LL is the LDM recovered bits. So this part bits combined with your index bits, you just recovered from the detection of the active channels, 1 and 0, you have your overall bits. So the overall original bits will be your 1, 0 combined with the recovered LDM bits. So in this case, besides the traditional LDM part, we don't do any extra work, but we can have the index information to bury into the transmission part. So at the transmission, at the same time, we have the index information and also used for the LDM information to provide more capacity, to support more capacity or throughput for the channel. However, what's the error performance? So now we consider the error performance regards the LDM systems. So here, the error performance, we consider the model with the received signal Y or received symbol YUL actually is equivalent the two parts. So the transmitted XUL is the transmitted up layer and the transmitted low layer combined with the channel. And this actually also equivalent to your up layer, because your up layer actually is your overall received signal. This includes your up layer signal itself, also include the low layer interference. So we can consider the conditional, the symbol performance, error performance. We just need, as this is as a conditional probability of your XUL and the received or estimated XUL under the channel HUL condition. So this will be actually the distance. So if you consider the maximum likelihood ML detection, this condition will be the two distance larger the received signal to the distance of the recovered channel effect larger than the estimated signals. Okay. So in a simple word, we can derive the up layer condition error rate and also for the lower layer condition error rate. So I want to talk about the simulation. So these two equations, we develop purely the closed form, so we can have a closed form for the error performance for the LDM and the IM modulation. So how is performance considered with a closed theoretical result and also the simulation result? So in this case, okay, we construct the simulation first. So the simulation is a dot. So this is an individual dot is a purely simulation. So we just sending our data using the two modulation and the simulation scenario with a Monte Carlo simulation, and we can have this dot results with a power over the noise per channel. And this is very close to our theoretic result curve. And this curve here actually is purely based on our closed form expression. So that means our theoretical result is perfect estimate the simulation results. And here we use the frequency selective Rayleigh feeding channel. So this classic channel. And also use for BPSK for the both up layer and the low layer. And there's two UEs, so two users. So we only got two layers, so we can support the two users at the same time. And so that's why the two users, we have the same path loss, but with the two IID channel, the two channel profiles are different. But the user path loss with exponential decayed path loss model. And also in the transmission, okay, the transmission rates, we simulated our proposed LDM-IM have a better transmission rate per channel, per use channel. So especially when you increase the size of FFT, you can get a better performance. So this is a summary, and any questions?